only the knowledgeable person transfers or shares his ideas to the learners of this society. Today among us, we have one such knowledgeable and inspiring person. She is Dr. Anita Sengupta, Project Director of Cold Atom Laboratory, NASA, and Jet Propulsion Laboratory, USA. She is here to enlighten us about space exploration and to spread her knowledge about space science to us. So let us know more about our chief guest. I would like to call upon Arvind Nair, GM.
An eminent scholar and an engineer, Dr. Anita Sengupta amidst us. It's my great pleasure to introduce her to all of you. Dr. Anita Sengupta is an engineer at NASA's Jet Propulsion Laboratory. She played a key role in the historic landing of NASA's 110 Curiosity rover on the Red Planet on August 6, 2012. Dr. Anita has been developing entry system and propulsion technologies for Mars, Venus, and deep space missions for the past decade. She is currently the project manager for the Cold Atom Laboratory mission, an ultra-cold quantum gas experiment to be launched into the International Space Station in 2016. In her earlier roles, Dr. Anita has held various responsibilities. She was the lead systems engineer for the MSL supersonic parachute, leading the development of a Mars ascent vehicle, the principal investigator for the Orion vehicle drop parachute subscale test program, entry system phase lead for a Venus lander mission, lead systems engineer for a Mars sample return mission concept, and co-investigator of several plasma propulsion development programs, including BHITAL, NEXIS, and Prometheus-1. Prior to joining JPL, Dr. Anita worked in industry on the Delta IV launch vehicle, X-37 vehicle, space shuttle, and commercial communication satellites. Dr. Anita received her BS as Bachelor of Science in Aerospace Engineering from Boston University. And further not, she was famous and loves motorcycle riding and scuba diving. Her interests also include community service, politics, and world traveling. She has to her credit numerous honors and awards like JPL Mariner Award in 2009, JPL Spot Award 2009, NASA Tech Award for Method of Doubling Xenon Thruster Life in 2007, ASEI Women Engineer of the Year recipient in 2006, JPL Team Award, Nexus Ion Thruster Technology Program in 2005, and so on. I know this is not enough to introduce her, such a great scientist, yet sooner you are going to hear her voice in her words. May I now request Sri Maheshwarya ji to hand over the bouquet to Dr. Anita Sengupta as a token of appreciation. I heartily welcome everyone. We also have Sri Arvind from Seva International. I request Principal Srimati Pushpa Rudrashna to hand out the bouquet. I also welcome Abraham for this occasion. I just want to give a brief introduction of him. He is Principal Scientist at Biotechnological Company Anvin. His main work is to translate research to chemical practice. I also welcome you. I request Maheshwarya ji to hand out the bouquets. Just like the branches of tree called Rashdotana, we have our correspondent Sri Maheshwarya ji. I also welcome you, sir. Principal of Rashdotana PV College, Srimati Pushpa Rudrashna, and Principal of RVKB, Srimati Manjula ji. Also welcome. We have also, I welcome all my dear
On space science. Now I request Dr. Anita Sengupta to take over the session.
Good morning, everyone, or good afternoon. I'm happy to be here. I'm going to try and get a hand mic so I don't have to be stuck behind the podium because I'm very short if you can't see me. That's why I like to wear heels. So my family lives in Kolkata, and I was fortunate to go visit them a couple of days ago. I've been in India for a week now, and I'm kind of doing a circuit around the country talking about space exploration, specifically Mars exploration. And so now I'm in Bangalore speaking to you, and I'm speaking at ISRO tomorrow. Laboratory. So all of you are probably familiar with NASA, National Aeronautics and Space Administration. We have many different NASA centers. I work at JPL for short, and we do rovers. You can see what the rover has been doing. So you can see it driving a little bit, then it stops to make a measurement with this robotic arm. You can see its tire tracks. You can also see in this image, it's now scooping the soil. You see those little black bits in the middle there? There's little scoops that it's made in the soil to collect the materials. So it puts itself inside an easy bake oven. And basically, it kind of looks like a transformer. That's what I think when I see its shadow. And this is what its job is for the next 2 years. And we communicate with the rover twice per day and send it commands that we want you to do this, tell us how you're doing, and then it goes off and does it. And we communicate with it again later that day, telling it its plans for the next day. And this is how the mission goes forward. So we have at least 1 year left of science ahead of us, and probably many years to come after that. It's been a really fascinating mission. All the data that we collect is actually on the web. It goes onto the website. It's for everybody to share. It's for everybody to look at. So you're free to make any kind of analysis off of the images that you can see here yourselves, because that's the reason why we're doing this mission, is for everybody, not just for NASA scientists or people in the United States, for anybody who's interested in Mars exploration. And these missions are actually usually very much international endeavors in terms of the science measurements that are made. And so we can go to the next one. So just to wrap it up, all of the information on this mission you can find online on our websites. I encourage you to look it up. You can download all the images, all the movies. You can even download some of the graphs that I showed you for like chemical compositions. And so it's intended to get everybody involved. And just to understand how it is that we tried to get students involved, Curiosity, the name of the rover, was actually selected by, I think, a 5th grade girl called Clara Ma in Kansas, in the United States. And so we had a competition where we involved all of the students, and then we ended up selecting her name.
Space engineer, what was your greatest inspiration?
Oh, thanks. So I've had 2 sorts of inspirations. So my dad was a mechanical engineer. My dad actually got one of his degrees at IIT Bombay. So for those of you who are studying to be in the IIT schools, my dad always told me it's incredibly difficult, but it's one of the best trainings that you can get. I'm an inspirational, just the way engineers solve problems differently than everybody else. So scientists and engineers are quite different from each other, actually. So I really like being an engineer because it means that you come up with new and innovative solutions to solve the world's problems, pretty much, whether they be technological, hardware, or software. But the real reason why I wanted to get into space exploration is because I was a huge fan of science fiction as a kid. And so I watched Star Trek, Doctor Who, Star Wars, and I knew I wanted to be involved in space exploration. And so for me, it was a choice of, did I do aerospace engineering, astrophysics, astronomy, physics? And I ended up choosing aerospace engineering because I liked the idea of building new technologies. And so but I always knew, ever since I was probably about 6, that I wanted to do something in the space business. I just had to choose what the right degree program was for me. But I think engineering is a wonderful field to go into, whether it's electrical, mechanical, aerospace, civil, any of the engineering fields is probably the best training you're ever going to get in life. Even if you choose to do something else afterwards, like medicine or law, I highly recommend engineering.
The you ma'am is from Aditya, first PUC. He wants to know, rover does not use solar energy, instead uses radioactive isotope for electricity generation. Why it is so? In case if the radioactive isotope gets exhausted, is there any other alternative source for energy?
So our prior rovers, Mars Pathfinder, Mission Sojourner, and the Spirit and Opportunity Mars Exploration rovers, they did use solar panels. And so the advantage of solar panels, of course, is that you're using energy from the sun. The disadvantage is that on Mars you have dust storms. And so those solar panels become covered in dust almost immediately. So your power degrades over time rather significantly. Solar rays also tend to degrade in a radiation environment, so they have a pretty limited life associated with them on Mars. It's still okay, but you don't have as much power. You're also limited by the solar angles. You can't go to as intense latitude as you could with a mission that didn't rely on solar power, and you also can only operate over a few hours a day. So when you go with an RTG system, which is this radioisotope thermoelectric generator, you actually have a more consistent power source, which isn't affected by the amount of solar radiation that you see, and it isn't affected by any kind of dust deposition. So it actually makes you a more capable rover. In terms of the half-life of the radioactive material that we selected, it's a very long time, so something else on the rover will actually die before that ever runs out. So for example, we have our deep space missions at JPL and NASA, which are basically leaving the solar system right now. They had an RTG. They're still powered over 30 years ago. So that isn't an issue for us in terms of running out of power, because it lasts a really long time because of the long half-life.
What has been your biggest challenge and your biggest achievement so far? Was your most challenging moment your happiest moment?
challenging, so it's always difficult, and that's the reason why we do it. So the whole reason why we did this thing is because we knew it was going to be hard, but that's a good reason to do it. So everything that we do where I work is difficult. Everything is challenging. If it was easy, we wouldn't do it. I wouldn't want to do it personally. It would be a boring job. So I would say any mission that I've worked on has had tremendous challenges associated with it, but that's the reason why I'm doing it. So for example, during the parachute development, we ran into all kinds of problems where the very first test, the parachute failed, it wasn't strong enough, so we redesigned it, we made it stronger. When we were doing the supersonic test, we had great difficulty in deploying it because it has to happen over a really short period of time when we came up with a solution for that. But that was fun for me. So the fun part was actually overcoming these problems. So I would say everything's been a challenge, and but that's what makes it enjoyable. And I forgot the second part was, I don't remember.
He wants to know what are the major technical advancements incorporated in Curiosity and rover mission as compared to previous attempts.
Control system. So on prior entries, we were ballistic entries, which means we weren't a lifting body. In this particular mission, we actually had an angle of attack. So that odd-looking bowl-shaped body actually had an angle of attack. It was kind of like an airplane, if you want to think about it, a hardly efficient airplane, but an airplane nonetheless. And so we were able to fly the thing down to the surface. Now, we didn't do it ourselves. It was an autonomous system. But by changing the bank angle on it, we were able to fly it down to increase our altitude margin above the surface. So the guidance navigation control system is called hypersonic guidance, which was probably the biggest, in my opinion, probably the biggest wonderful, successful engineering improvement on this mission. And then, of course, the skycrane maneuver. We had never done that before. And so there's also guidance navigation control associated with the skycrane maneuver, where you actually have to operate these throttleable engines to be able to tilt yourself to fly to where it is that you want to go. So those, I think, will probably, to be honest with you, every aspect of the mission was a leap forward from the prior mission that we did. So whether it be in parachute development and engine technology and heat shield technology, they were all advancements over what was done over the state of the art. And so when you do these missions, that's just what it is. You have to advance the state of the art for each mission. But what I can say though is that that's what makes it fun. So it's interesting.
He wants to know, if I take aeronautical engineering, what are the career opportunities open for me?
Well, I can't speak for India just because I don't work in India, but I can mean aircraft development, or it can mean spacecraft development, or in some cases it can also mean ship development for seafaring applications. So I can only imagine there's plenty of opportunities. We have a launch coming up next week, the launch vehicle, so you obviously have a lot of opportunities in the launch vehicle too. We have a mission to Mars launching this fall, so I think you have a lot going on here in aerospace, specifically in civilian space. So that's why I think you actually have a lot of opportunities. So I encourage you to pursue aerospace if it's something that's of interest to you. In general, you should choose the degree, which is what you want to do later on. You shouldn't choose the path that somebody else tells you to take and where you think you're going to get the best job. You should choose the field that interests you, that you feel passionate about. And then everything else will follow.
Where can we find more technological information on NASA's research? This is from Shreya.
Oh, so we have everything online. So if you go to, like, if it's Mars.jpub.nasa.gov, you can find out about the mission. You should be able to find out about the different aspects of the entry, descent, and landing vehicle. All of us as engineers, we actually write technical papers. And so you can go search on Google if you have something you're interested in. Like, if you say parachute and Sengupta, you'll find like tons of links to articles that I've written, for example. And the same goes for any of the things that I just showed you. We do write a lot of technical papers. So if you want to just know high-level stuff, you can go to the website. If you want more detail, then you can get papers from like AIAA, IEEE, and it's all public domain material. So you have access to it. So if you go through your library or ask, I don't know whether or not you have access to the online databases, I'm assuming you do. But if you need help, you can just ask your librarian to help you. But there's a wealth of information out there if you want it as a high schooler, and certainly if you want it as a college student.
Preparing to get accepted.
Oh, well, let's see. I didn't really have a university in particular that I wanted to go to. I wanted to go and study aerospace engineering with a spacecraft focus. Now also, go with the one that gives you the most scholarship money. So I went with Boston University because they basically, covered all of my tuition, so I didn't have to pay for it. So that, to help your parents out, if you can get a scholarship out, it's all. Otherwise, they end up paying for everything. But it really doesn't matter necessarily which school you go to. It has to have the program that you're interested in. So if you want to do an aerospace degree, if it's got a good aerospace program, that's where you should go. If you want to do electrical engineering, go to a school with a good electrical engineering program. So it's about getting the training, understanding the core fundamentals. And then after you get your undergraduate degree, then you go on and do an advanced degree. So I did my undergraduate at Boston University, and I did my master's and my PhD at University of Southern California. And I picked USC specifically because they had an astronautics program. So they focused on spacecraft design. And so now I teach there, actually. So now I'm full circle. Was a student, now I'm teaching people. So it's not about the name of the school, it's about that it has the program that you're interested in.